If you've ever watched Shark Week on the Discovery Channel, you may have seen awesome video footage such as this. Great white sharks near the coast of South Africa are notorious for breaching or jumping out of the water while attacking seals. Great white sharks can grow up to 20 feet in length and weigh more than 5,000 pounds. So being hit by a breaching shark is comparable to being hit by a full-size truck. Let's read the question. A great white shark can reach a height of 2.5 meters above the surface of the ocean when breaching. A. What was the shark's initial velocity when it left the water? And B. What was the shark's hang time? Upon watching this video, you might be thinking to yourself, that seems like a really complex motion as the shark jumps out of the water and twists in the air. Can we use the kinematics equations to analyze the shark's motion? And the short answer is yes. By focusing on the shark's center of mass, we can imagine the shark as being a point particle because its center of mass acts like any other freely falling object that we could consider. In fact, the same goes for wrenches, boomerangs, humans, footballs, or any other macroscopic objects that you can imagine. Of course, we must also assume that air resistance is negligible, and it obviously is in this situation. The first step is typically to draw a picture, or as I did, Google and label a picture. Take a look at all of the variables that we need to consider, and notice that we were provided no time data for this situation. Part B requires us to find the hang time of the shark, but any kinematics equation that you look at involving time also involves initial velocity. Here's the proof. If you take a look at the two equations that I've written on the screen, you see that time is involved in both equations, but so is initial velocity. And we do not know the initial velocity as I've labeled right here. Therefore, we should probably start off by considering a time-independent kinematics equation. Another thing that's helpful to know is that at the maximum height, the shark's velocity is switching from positive, or upward, to negative, or back down towards the water. Therefore, at the maximal height, the shark's velocity is 0. So, let's solve part A. What was the shark's initial velocity when it left the water? Let's use our time-independent kinematics equation, and let's also remember that at the maximum height, the velocity of the shark is equal to 0. Here is the kinematics equation that I'm talking about. As you can see, there is no time variable in this equation. We do have a final velocity, an initial velocity, an acceleration, and a displacement symbol. We know the shark's displacement at the maximum height. It's shown in the picture as 2.5 meters. We know that the acceleration due to gravity here on Earth is negative 9.8 meters per second, or negative 9.8 meters per second squared. And we also know that at the shark's maximum height, the velocity is equal to 0. The only thing I don't know in that equation is the initial velocity. And of course, that's what I'm being asked to solve. So let's plug in all of the information that we know. All of the numbers that you see that I've plugged in are considering the position shown, the maximum height of the shark. The shark's velocity at the maximum height is 0. It is 2.5 meters above the surface of the water, and of course, it is accelerating under the influence of gravity. To solve for the initial velocity, all you have to do is the algebra at this point. Notice that my units are meters squared per second squared for the term that you see that's 2 times negative 9.8 times 2.5, because meters times meters on top gives you meters squared, and of course you have a second squared unit in the denominator. And to simplify this, add the 49 meters squared per second squared to the other side, and we can take the square root of both sides and solve for the initial velocity. I've kept those awkward units in there just to show you that when you take the square root of both sides, the units will come out in the proper units for velocity. By taking the square root, we can simply evaluate the square root of 49 to be 7. And if you take the square root of meters squared in that numerator, you get just meters. And if you take the square root of seconds squared in the denominator, you get just seconds. So therefore, the initial velocity of the shark as it left the water was 7 meters per second. We have a final answer. One interesting note about that number is that it's about equivalent to 16 miles per hour. Remember that a 5,000 pound creature coming at you at 16 miles per hour can deliver quite a punch. There are actually multiple ways to solve part B, all of which should give you the correct answer if your reasoning is good. The first method is to realize that the shark leaves the water at the exact same height that it will re-enter the water. We can use our displacement equation, and by setting the displacement equal to 0 because the shark returns to its initial height, we can solve for the total hang time. In this equation, delta x will be 0 when the shark re-enters the water, and once again, that's because it is returning to the exact same height that it initially left the water. For the sake of time, I've simplified things a little bit. I've plugged in 7 for the initial velocity, and I've taken 1/2 of the acceleration due to gravity. 1/2 of negative 9.8 gave me negative 4.9, and of course the variable t squared and t, those are the time variables that we're trying to solve for. You don't need to use the quadratic equation here, because if you notice, the two terms that you're left with each have a t in them. Let's factor out a t from the two terms on the right-hand side of the equation. There are going to be two answers here. The first answer is very simple. What number could you plug in right here for t to give you an answer of 0? Well, that's pretty simple. We could plug in t equals 0, because when you take 0 and multiply it by what's left in the parentheses, I don't care what's in the parentheses, 0 times anything gives you 0. So one answer is t equals 0, but we kind of already knew that. Obviously, the shark's displacement was 0 meters above the surface of the water at time equals 0. Based on the problem, as we have it over on my picture, we're more concerned with the time that's going to come by setting the parenthesis term equal to 0. So let me show you how we do that algebraically. All I did was set what's inside of the parentheses equal to 0, and I will solve it by adding 4.9t to the right-hand side of the equation. And at this point, all I have is 7 equals 4.9t. If you divide both sides of the equation by 4.9, you will get a time value of 1.4 seconds. What this means is the shark at time t equals 0 was at a height of 0, and the shark came back to that same height and re-entered the water at t equals 1.4 seconds. Very briefly, I'll show you a second way to solve this problem, but there are actually more than just two ways. The other approach would have been to use the equation Vf equals the initial velocity plus acceleration times time. We can use this method because the shark left the water with an initial velocity of positive 7 meters per second, and it returns to the same height. So its velocity will not have the exact same numerical value, but it will be in the opposite direction. Instead of being positive 7 meters per second, it will be negative 7 meters per second. The shark's motion is symmetric because the displacement as a function of time creates a parabola as the shark falls under the influence of gravity. If we use the equation shown on the screen and substitute in the initial velocity as positive 7 meters per second, the final velocity as the shark re-enters the water will be negative 7 meters per second, and the acceleration due to gravity as negative 9.8 meters per second squared. Here's what it'll look like. Because I'm running out of space, I've neglected to use units, although I strongly recommend that you use your units and significant figures throughout your calculation. At this point, I could subtract 7 from each side of the equation, and what I end up with is negative 14 equals negative 9.8t, and by simply dividing both sides by negative 9.8, you will see that you get the exact same time of 1.4 seconds for the shark's hang time. I hope you found this video helpful. Please share it with your other physics friends, and if you have any other questions, please stop in and see me.